right, so today we're going to talk about Module 2, and we're going to talk about probability. And again, these are taken from the lecture notes from Module 2. And we just start out with some definition, and it says that the probability is just a measure of the likelihood that a given event will occur. All right. And it's expressed between a number as 0 through 1, right? Probabilities can never be negative, and they can never exceed 1. All right, so the probability are trapped in between 0 and 1. Now here's just some notations for probability. You're going to see a capital P, and that's going to denote probability and the probability of an event happening or is likely to happen. And then we have capital A, B, C. You can have a capital D, E, or F. And those are just notations for specific events. So when you see a probability written out, you're going to see this P of A, and that denotes the probability of some event occurring. So like you're going to see find the probability of rolling a 1. Okay, so A could be rolling a 1. You may see the probability written out like this, the probability of A, B, or C, or they could be written out in actual sentences or phrases. All right, so with just that first definition, I am going to pull up the handout, and this is just that Module 2 handout part 1. And this first question asks us, which of the following values could not be a probability? So we're just giving some numbers. We're given 8. We're given 6/7. We're given negative 0.1611. We're given the square root of 10. And we're also given the square root of 1/7. So we are asked to determine which one could not be a probability. All right, so I'm just going to bring up the calculator. And I'm just going to decimalize these values. And if the decimalized values are outside of 0 and 1, then it could not be defined as a probability. So let me just close that down. All right, so look at the first one, 8. Could 8 not be a probability? Right, that would be considered an answer choice, right? Because 8, it exceeds 1. That means that it could not be a probability. All right, and I can't actually write on this. All right, so we have 8. (6/7) negative 0.1611. All right, so 8 is not a probability, right? So what about 6/7? Well, if we put 6/7 into the calculator, just clear that out. 6 divided by 7 is 0.857. So that actually could be a probability, all right, because it falls in between 0 and 1. So notice that the definitions here are which could not be a probability, right? So 8 could not be a probability. What about negative 0.1611? That's not a probability because probabilities cannot be negative. Right? What about the square root of 10? Well, if we were to evaluate the square root of 10 into the calculator, all right, we get 3.16. So that is not a probability value. And then the last one, the square root of 1 over 7. So I'm going to just put that into the calculator and decimalize it. The square root of 1 divided by 7. And that is 0.38. And that could be a probability value. Right? So my answers here are 8, negative 0.1611, and the square root of 10, all of which could not be probabilities. Okay. So as we begin, just keep in mind that a probability has to be in between 0 and 1. It can never be negative, and it can never exceed 1. Right? So when we look at these probability distributions in the future, you should be able to add up all of the probabilities, and they should be exactly 1. Okay, so we'll talk about that later. All right, now we have the classical approach to probability, right? And this is basically a formula. It says assume that a given procedure has n different simple events. Okay. And that each of those simple events has an equal chance of occurring. If the event A can occur in S ways, then we have the probability of A, which would be that probability of the event happening, would equal to the number of ways the event can occur divided by the number of different simple events. Now, if you think about a fraction is a part over the whole. A probability and a fraction have a similar relationship. So when we think about a probability, we think about all of the different ways that an event can occur, right? That would be the whole. And then the part would be the specific events that we want to occur. So now as this definition, the probability of A is equal to S over N. So A is the number of ways an event can occur, and N is the number of different sample events. And here's an example. It says in a study of brand recognition, 1,001 customers knew of McDonald's, and 32 customers have never heard of McDonald's. Use the results to estimate the probability that a randomly selected customer will recognize McDonald's. So we're going to use this probability formula. So as far as the probability is concerned, I would generally tend to start with the total, the denominator, right, which would be the number of different simple events. So if we look at this example, we're looking at customers, right, the total amount of customers. So we had 1,001 customers that knew of McDonald's and 31 customers that did not know of McDonald's. So altogether, we have how many customers? Well, we're going to add those two things together, right? Okay, and on the handout, I believe this is actually number 4. Just to show what this is. You're on the handout, this is actually number 4. And is there a way I can? Okay, I have to experiment with this later. I thought it was a way I can actually open this up so I can write on it, but anyway. All right, so this is actually number 4. All right, so the first thing I want to figure out, what is the total number of customers, right? So that's my denominator. So I have 1,001 people that did not know of McDonald's, plus there were 32 people well, 1,001 people who knew of McDonald's, and then there were 32 people that did not know of McDonald's. So that's my base total. That's my total amount of customers. In the numerator, I only want the customers that recognize McDonald's. So how many customers recognize McDonald's? Right. Well, from the question, it says 1,001 customers. So this gives us our probability. So I have 1,001 divided by 1,033, right? Because there were 1,001 customers that recognized McDonald's. The total number of customers were the 1,001 that recognized plus the 32 that did not recognize McDonald's. So if we put this into the calculator, 1,001 divided by 1,033, we get 0.969. Okay. And in the direction, they want us to round to 3 decimal places. All right, so any questions about that example? Okay, now at this time, I would like for you to attempt problem number 2. It's like the same concept, just a different type problem. It says, if a pencil is drawn randomly from a jar that contains 7 orange pencils, 6 red pencils, and 17 purple pencils, find the probability of the following events. A, an orange pencil is drawn. B, a red pencil is drawn. C, a purple pencil is drawn. D, a black pencil is drawn. And then E, an orange or red pencil is drawn. So we'll kind of go through A together just to know where you're headed on this. So first of all, we need to know the total amount of pencils that we can choose from. That's our denominator. All right, so we have 7 orange pencils. And I wish I could really write on this. So this is number 2. We need the total number of pencils. All right, so we have 7 orange pencils plus 6 red pencils plus 17 purple pencils. So that gives us a total of 30 pencils to choose from, right? So that's going to be our denominator. There's 30 pencils in this jar, right? That's our base total. The first one says the probability of an orange pencil is drawn, right? Well, how many orange pencils are in the jar? 7, right? So the probability of drawing an orange pencil is going to be what? Well, how many ways can I draw? Well, first of all, the base is 30 pencils, right? The numerator is how many choices of orange pencils do I have? 7. So that's the probability, 7 over 30, right? Because there's 7 orange pencils, there's 30 pencils total. So the probability of drawing an orange pencil would be 7 over 30. So if we put that into the calculator, I believe you get 0.233. All right, so at this time, I would like for you to complete B through E. And so I'll give you a few minutes to figure those out, and then we're going to take a look at the solutions. And I'm going to actually write these out. Right, so let's take a look at the solutions. Okay, so what would be the probability of drawing a red pencil? Anybody? 6/30, right? Because there's 6 red pencils, 30 pencils total, and that is 0.2, right? What is the probability of purple? 17/30, right? Because there's a total of 17 purple pencils, and then the total amount of pencils in the jar is 30. And rounded to 3 decimal places is 0.567. And just a little calculator trick really quick, if I could turn this thing on. All right, if I put in 17 divided by 30, right, notice it gives me 0.5666667. You can actually force the calculator to round to however many decimal places you want. So let me just show you that really quick. If I were to go into mode, and for this second line where you see float, float means that it's going to list out all of the decimals as far as how many digits the calculator can store. But if you want to specifically, let's say, round the 3 decimal places, I can actually go over and change that to a 3. If you want to round to 4 decimal places, you can put it at 4. The only thing about this is, after you finish, you want to change it back to float. If not, anything you put into the calculator is going to round it to 3 decimal places. All right, so I'm going to just leave this at 3. And now if I go back and if I were to put in 17 divided by 30, right, it's just going to automatically round to 3 decimal places. All right, what is the probability of drawing a black pencil? 0, right? Because there are 0 black pencils, 30 pencils total. 0 divided by 30 is 0. Now, what about the last one? What's the probability of drawing an orange or a red pencil? Right, well, the denominator is 30, right? Because there's 30 pencils. How many orange pencils can we choose from? 7, right? Plus, how many red pencils can we choose from? 6. So that probability is 13 divided by 30. So I simply added the number of orange pencils, added the number of red pencils, right, to get the number of ways you can choose an orange or a red. So 13 divided by 30 should be 0.433. All right, any questions about number 2? Because in some of these things, you're going to see the word or, some of these things, you're going to see the word and. Some of the probabilities, you add them up, and then other ones, you multiply. All right. Okay, but just to start, we're finding single probabilities, the probability of an event happening. All right, I'm going to go back to the handout, and okay, I would like for you to do number 3, I believe this is. All right, it says answer the following questions based on the spinner below. You may assume that each region of the spinner is equally likely. Okay, they're all spaced out equally. It says you may give your answers as fractions or decimal rounded to 3 decimal places. So the first one says that the probability that the spinner lands on 1. The second one says the probability the spinner lands on 8 or 7, right, which was similar to that last problem. The probability that the spinner lands on an odd number, the probability that the spinner lands on a multiple of 9, the probability that the spinner lands on a number greater than 2. And then lastly, the probability that the spinner lands on a number less than or equal to 5. All right, so at this time, I'm going to give you a few minutes to, attempt this problem, and then we're going to take a look at the solution. All right, so let's take a look at the example. All right, so what would be my base total for this? Well, the base total would be how many numbers are there to choose from. All right, so there's 12 numbers. So the number of ways each event can occur is 12, right? Because there's 12 numbers. So the probability that the spinner lands on 1. Well, how many ones are in the spinner? Just 1, right? So the probability of a 1 would be what? 1 over 12, which is 0.167. Come on, 1 divided by 12. 0.083. The probability that the spinner lands on an 8 or a 7. Anybody? 15. Okay, now if we go back, so if you look at a 7, there's only one 7. And if you look at the 8, there's only one 8. Right? So that probability would be 2 over 12. Okay. So we're not actually adding up the numbers, we're just looking at, can you all see that? We're just looking at how many spots the 8 occupies, or how many spots each number occupies. So there's only one choice of 8, only one choice of 7. So that's 2 over 12, which is 0.167. So what's the probability that it lands on an odd number? 6 over 12, right? Because there are 6 odd numbers, right? 1, 3, 5, 7, 9, 11. So 6 over 12 is a half, 0.5. What's the probability that it lands on a multiple of 9? Right, 1 out of 12. So remember, a multiple, like the multiples of 9 would be 9 times 1, which is 9, 9 times 2, which is 18, 27, 36. Okay, on a spinner, it only goes up to 12. So there's only one multiple of 9, right, which is 9. So that probability is 1 over 12, right, which again is that 0.083. Okay, so what's the probability that the number lands, that the spinner lands on a number greater than 2? Right. So now, since it's greater than 2, I'm not going to choose 1. I'm not going to choose 2 because 2 is not greater than 2. Now, if it says greater than or equal to 2, I would choose 2. But the numbers that are greater than 2 would be 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that gives us a choice of how many numbers? 10. So that probability is 10 over 12, which is 0.833. So without the word equal to, you don't actually use that number. So if you look at the last one, it says the probability of the spinner that lands on a number less than or equal to 5. So in that case, you would choose 5, 4, 3, 2, and 1, which would give us a total of how many numbers? 5, right? 1, 2, 3, 4, 5. You would actually include 5. So that probability is 5 over 12, which is 0.417. All right, so any questions about just probability in general? It's the number of ways an event can occur divided by all of the ways an event can occur. Okay, so sort of like a fraction, a part over the whole. All right, so next we're going to talk about independent and dependent events. Okay, now for something to be dependent, it would have to depend upon something else happening before it can happen. If something is independent, that means one event doesn't affect another event. Okay, so let's take a look at the definition and then some examples. So it says for dependent events, events for which the occurrence of any one event affects the probability of the other event happening. Examples of that would be the event of having your car start and getting to your statistics class on time. Right? That happened to me. That happened to me. All right, so they was dependent. The car didn't start, so I didn't get to class on time. Right? Those things were dependent. Independent events are events which one occurrence doesn't affect the probability of something else happening. An example says playing the New York lottery and then playing the California lottery are two independent events because one lottery doesn't have any effect on the other lottery, okay, because they're two different events altogether. Okay. So that's pretty much the takeaway from dependent and independent events. So we're going to see how those actually work in a statistics problem. All right, I want to talk about the fundamental counting rule. And it says for a sequence of two or more events, so like the stuff we just did, it was like the event of one thing like happening. Okay. When we deal with the fundamental counting rule, we're dealing with a sequence of two or more events. And it says that the first event can occur m ways. Now it says actually two events, but we're going to see in a second that this can be telescoped out to more than two events. The first event can occur m ways. The second event can occur n ways. The events together can occur a total of m times n ways. All right, which means you can multiply. The fundamental counting rule easily extends to situations involving more than two events, okay, as illustrated in this example. And this is a license plate example. It says license plates in Wyoming consist of two letters followed by 4 digits. How many different license plates are possible in Wyoming? So this is an example, and this was the number of license. Okay, 2 letters and 4 digits. So it was 2 letters and 4 digits. So altogether, that's a total of 6 characters, right? So I'm going to map it out like this. So the first character is a letter choice times the second character is a letter choice times 4 number choices. 1, 2, 3, 4. So that's a total of 6 characters altogether, right? 2 characters are letters, and then the last 4 digits. So for the first choice, this has to be a letter. How many letters in the alphabet? 26 choices, right? You can have A through Z, which is 26. So for the first choice of character, I can have 26 letters to choose from. The second choice is also a letter. So again, how many letters in the alphabet? 26. Because it didn't say anything about the letters couldn't repeat. It just says that it's 2 letters and 4 numbers. So if we look at the third character, that has to be a number. And how many numbers do we have to choose from? We got 0 through 9, which is a total of how many numbers? We got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 numbers to choose from. The fourth character is also a number. Right. The fifth and sixth characters are also numbers. To find the total number of license plates, we're just going to multiply all of these numbers together. 26 times 26 times 10 times 10 times 10 times 10. All right. So I'm going to do that here. So I guess to write this out algebraically, even though this is not an algebra class, I can write this as 26 squared, right? Because 26 times 26 is 26 squared times 10 to the fourth power. Because 10 times 10 times 10 times 10 would be 10 to the fourth power. So I'm going to put this in the calculator as 26 squared times 10 to the fourth power. And see, it's still rounding the 3 decimal places. So I'm going to go into the mode and I'm going to put this on float. And now if I go back in and calculate it, it should not round the 3 decimal places. All right. So that is 6, 7, 6, 1, 2, 3, 4. So that is 6,760,000 choice of license plates. So you can figure that up for South Carolina. So I'm not actually from South Carolina, but how many characters are there? And then if you take the number of letters, I know in Georgia it's 3 letters, 3 numbers. 13. You can also figure phone numbers, right? The phone number for us, what? It's 10 digits, right? It is 10. Yeah, 803 508 7466. So it'd be a choice of 10 numbers for all 10 choices. You can even do social security numbers. I think they're kind of running out of social, but I ain't gonna say running out of social security numbers, but like during my time period, the first 3 numbers for my social security number are totally different than the first 3 numbers for my kid's social security number. So like my social security number, my sister's social security number are about the same 3 digits for the start, right? But you can do that as well, right? Because I think it's what 9. It's 9 digits in a social security number. So you would have the first choice would be 10 numbers, second is 10, third is 10. Okay, so that's the fundamental principle of counting. All right. And then that's why the phone numbers, I ain't gonna say the phone numbers are running out, but you notice the area code changes. Because some of the area codes are like 843 for South Carolina, some of them are 803 for South Carolina. All right. But all that's dependent upon the fundamental rule of counting. Okay. Now we're going to use this and look at some problems. Okay, the first one is number 5, and this is on the handout. Okay, So I'm actually going to go through 5 and 6, okay, and then we'll take a look at the rest. Okay, this is number 5. It says a study reports that 70% of all people own cars. Suppose that 3 people are chosen at random from a population, right? So the statistic is that 70% of all people own cars. So if you were to randomly choose 3 people, right, they want us to answer the following questions. Are the events dependent or independent? B asks for why. C asks for the probability that all 3 own cars. So let's take the first one. Are the events dependent or independent? So what does that mean? So let's just say everybody in this class. So if I were to ask this gentleman if he owns a car or not, does that have anything to do with, let's say, this gentleman owning a car? It doesn't. There's no relation between the two. So these events are independent, right? Because one event doesn't, they're not brothers or related, I don't think. So there's no relationship between one or the other. All right, so they're independent. I can't actually write on this, so, but that's the answer to A, independent. B asks for why. The reason why, and then there's some choices. It says why, and it says select the answer. The first one says the people are chosen without replacement, and then it's supposed to be a period or something. And it says the people are chosen without replacement. C says there are many kinds of cars. The next one says a sample size is provided, and the last one says the events derive from a large population. The answer to why is that the events derive from a large population of people. That's what makes things sort of independent, because if you have a large population, then this person may not know this person, or this event doesn't affect the event of somebody, let's say in Alaska, doing a certain event. So the events derive from a large population. That's the reason why. C says, what is the probability that all 3 own a car? So here's where that fundamental principle of counting comes in. So I'm going to just kind of write this as a question onto itself. Example, 70% of people own cars. Find the probability that 3 randomly chosen people own cars. All right. All right, so 70% of people own cars. Find the probability that 3 randomly chosen people own cars. All right, so key word in this thing is randomly. So we're dealing with 3 people, right? So I have the first person, the second person, and the third person. Right? So what is the probability that the first person owns a car? Should be 70%, right? So 70% as a decimal is 0.7, right? What's the probability that a randomly chosen person, the second person, owns a car? Should still be 0.7, right? And then what's the probability that the third randomly chosen person owns a car? Still 0.7, right? Is everybody okay with that? Because we got 3 people. And it gives us the probability in the problem. It says 70% of the people own cars. So the probability that the first person owns a car has to be what? 70%. The probability that the second person owns a car would still have to be 70%. And then the probability that the third person owns a car would be 70%. So now what is the probability that 3 randomly chosen people own a car? We would have to do what to these numbers? Multiply them. So this would be 0.7 raised to the third power, which is 0.343. So that's 0.343. So is everybody okay with that? All right. So with the same problem now, and this is not on the sheet as far as this problem. Find the probability that 3 randomly chosen people do not own cars. So the same setup. Now I have 3 people. That's my first person, the probability for my second person, and the probability for my third person. So now if I go back to the original problem, it says that 70% of people own cars. So if 70% of people own cars, what percentage of people don't own cars? 30, right? Because you have to have that 100% total. So I'm going to put and 30% don't own cars. All right. So now if we go back to the randomly 3 chosen people, what's the probability that that first person does not own a car? Should be 30%, right? What's the probability that the second person does not own a car? It still has to be 30% because each probability is equal among every randomly chosen person because the probability is not going to change. So what's the probability that the third randomly chosen person does not own a car? It would still be 30%. So the probability that 3 randomly chosen people don't own cars will be 0.3 raised to the third power, which is 0.27. Oops. Okay. Oh, 0.027. 0.027. All right. Any questions about that problem? All right. So I use the fundamental rule of counting. So there were 3 people, right? So I put a blank for the probability of the first person times a blank for the probability of the second person times and then a blank probability for the third person. And then I just put in the probabilities for, in the first case, people owning cars, which was 70%, which is 0.7 as a decimal. And then for the second part, Okay, now this wasn't actually on the handout, at least not for this problem, right? But you had to figure out the probability of a person that does not own a car, which was 30%, and then we mapped it out the same way. Okay. All right, any questions about number 5? All right, now let's look at number 6. All right, and number 6 says, suppose a jar contains 10 orange marbles and 12 red marbles. If you reach in a jar and pull out 2 marbles at a time, at the same time, then answer the following questions. A says, are the events dependent or independent? B says, why? And 10 says, find the probability that both of the marbles are orange marbles. All right, so here's the setup. We have a jar, and in that jar we have 10 orange marbles and 12 red marbles, so that's a total of 22 marbles in the jar. We're reaching in the jar and we're getting 2 marbles at a time. Are those events dependent or independent? Dependent. They are dependent because why? So B says the marbles are drawn from the jar with a large number of marbles. The next choice says each marble is replaced before the next marble is drawn. The next choice says the total of marbles is known. The last choice says the marbles are chosen at the same time. The reason why is that the marbles are chosen at the same time. So if you take one marble, it's dependent upon the other marble, because if you take an orange marble, that kind of lessens the amount of orange marbles. Okay, so they're dependent because you're drawing each marble at the same time. Okay, C says find the probability that both of the marbles are orange. So I'm going to go back to OneNote. So we have 10 orange marbles and 12 red marbles in a jar. What is the probability that 2 orange marbles are drawn at the same time? Okay. All right. So we're going to do this counting principle thing again. All right. So what would be the probability, even though we're drawing both of these things at the same time, what would be the probability of drawing an orange marble, that the first marble is orange? That's right, that the first marble is orange. Right, where there's a total of 22 marbles and a total of orange marbles is what? 10. So the probability that the first marble is 10 out of 22, right? What's the probability that the second marble is orange?
9/21.
9/21. Okay, how did you get 21? That's right, because you're taking away from the total of 22 marbles. So my base is changing. All right, because I didn't take an orange marble out and then put it back in. So if you like, that's called with replacement. If you take something out and put it in, if you choose one at a time, that's with replacement. But in this case, we're taking two marbles at one time. So if the first marble is orange, then that has a probability of 10 over 22. So since the first marble is gone from the bag, that changes the amount of marbles that I have to choose from. So it goes from 22 to 21. And since the first marble was orange, it takes away from the total number of orange marbles in the bag. So in order to find this probability, I'm simply going to multiply the numerators. So 10 times 9 is 90. I'm going to multiply the denominators. 22 times 21 is 462. And if you divide, I believe you get 0.195. Is everybody okay with that one? All right, so now at this time, I would like for you to do problem number, I think it's number 7, or is it 8? Okay, I would like for you to do problem number 7 and problem number 8. Okay. All right, so problem number 7 says a dice is rolled twice. So they're talking about a 6-sided die. They don't mention that in the problem, but this is a 6-sided die because you do have dice that have more than 6 sides. Find, well, what is the probability of showing a 1 on the first roll and an odd number on the second roll? All right, that's number 7. Number 8 says Ethan has a bag of pencils, 6 white, 11 yellow, and 5 blue pencils. Find the following probabilities of Ethan drawing the given pencil from the bag if each pencil is removed from the bag after it's drawn. So when he takes a pencil, he don't put it back. All right. It says you may answer fractions or decimal rounded to 3 places. All right. So at this time, do number 7 and number 8. Okay, and then we're going to take a look at the solutions to those. Oh, where I was doing the writing on it? Okay. This one? Okay. All right, let's take a look at the example. All right, so the first one says a six-sided die is rolled twice. What is the probability of showing a 1 on the first roll and an odd number on the second roll? Well, before we start this, is this independent or is this dependent events? Does one roll affect the other roll? Yes or no? Should be independent, because if you roll a dice one time, you roll whatever you roll, then you pick it up, you roll again. So they're independent. So one roll does not affect another roll. All right, so it says that it's rolled twice. So I'm going to use that fundamental principle of counting. So it says that find the probability of rolling a 1 on the first roll. All right, well, we're dealing with a six-sided dice, right? 1 through 6. So there's a total of 6 possible numbers to choose from, 1 through 6. How many ways can you roll a 1? Well, there's only 1 on a six-sided dice, so that probability is 1/6. Right? Because there's 6 total numbers, just like the spinner almost, except it's on a dice. Right? 6 total numbers, there's only 1 1. Right? So that probability is 1/6. What's the probability of rolling an odd number? Well, again, there are 6 numbers altogether. So how many odd numbers? There's a 1, a 3, and a 5, which are 3 numbers. So the probability of rolling an odd number is 3/6. So now I'm just going to multiply the 2 fractions together. So whenever you multiply fractions, you multiply the numerators, multiply the denominators. So 1 times 3 is 3. 6 times 6 is 36. And 3 divided by 36 is 0.83. So that's the probability. Those things are independent. One roll, because you're just rolling one dice, right? One roll doesn't affect another roll. So any questions about that one? All right. All right, now number 8. And I've kind of reworded the direction some. It says Ethan has a bag of pencils. There are 6 white pencils, 11 yellow pencils, and 5 blue pencils. So that's going to give us a total of how many pencils? 22, right? So there are 22 pencils total to choose from. And it says find the following without replacement. So that means once a pencil is taken from the bag, it's not put back in the bag. Now, unlike that marble problem, I believe, okay, it really doesn't say if he's taking them 2 at a time or not, but it says find the probability that a white pencil is drawn and then a yellow pencil is drawn. Right, so I'm drawing 2 pencils. So I'm going to write out the probability for drawing a white pencil. So now the probability of choosing a white pencil, we're going to put the total number of pencils, which is 22. And then how many white pencils do we have? 6. So that probability is 6 divided by 22. Then we have to find the probability of choosing a yellow pencil. So now if we've chosen 1 pencil from the bag and we're not putting it back into the bag, how many pencils are total now in the bag? 21. Is everybody okay with it being 21? Because we took a pencil out, we're not putting it back in. So now there's a total of 21 pencils in the bag. So what's the probability of choosing a yellow pencil? 11. Right? So to figure out this probability, we're going to multiply the numerators. So 6 times 11 is 66. 22 times 21 is 462. And that gives us 0.143 for the probability. So remember that these probabilities are dependent. One event depends upon the other event. So that's one of the reasons why the denominator is changing. All right, so B says, again, we're drawing two pencils. So this is the probability for the first pencil, probability for the second pencil. So what's the probability that the first pencil is blue? Well, there's a total of 22 pencils in the bag. 5 are blue. So the first choice for a blue pencil is 5 over 22. So what is the probability that the second pencil is blue? 4 over 21, right? Because we've taken a blue pencil from the bag, so that lowers the amount of total pencils in the bag. And it also takes away one of the blue pencils, right? Because if the first one was blue, instead of having a choice of 5, we now have a choice of 4. So if we multiply the numerators, we get 20. We multiply the denominators, we get 462. And I believe that's 0.043. All right, so what about the last probability? So now we're choosing 3 pencils. A white, well, we're choosing 3 pencils. So I'm going to map out 3 probabilities. So what is the probability of choosing a white pencil? All right, 6 over 22. What's the probability that the second pencil is a white pencil? 5 over 21, right? And what's the probability that the third pencil is a yellow pencil? 11 over 20. So notice how the total amount of pencils is reducing by 1. So if we multiply 6 times 5 times 11, that's 330 divided by 9,240, which is 0.36. So there is a difference when the events are dependent and when the events are independent. All right, so I think we're going to stop here today. It's almost 11 o'clock. When we meet again next Wednesday, we'll take a look at the last 2, problem number 9. And we did one similar to 9, except for that very last and the probability of at least 1. And then we'll take a look at problem number 10, which deals with a contingency table. All right, and then we will kind of continue on. All right, any questions about anything up to this point? Was everybody able to take the test? How was the test? It was all right? Did the stuff in class help that we went through in class? Okay. All right, well, no further questions. You all have a good afternoon and see you all next Wednesday.